When a massive star dying, its own gravity forces the remaining material to collapse inward, compacting it into an impossibly dense neutron star. Imagine taking the entire mass of two suns and crushing them down into a single sphere no wider than a city. A single teaspoon of this material would weigh billions of tons. But there is a physical limit to this compression. Add just a little too much mass to a dying star, and the matter breaks. It skips the neutron star phase entirely, collapsing spacetime to form a black hole. Finding the exact mathematical dividing line between the densest physical matter and an inescapable void is one of the most persistent questions in modern astrophysics. Scientists have actually possessed the mathematical framework to calculate this limit for over 8 decades, dating back to the Tolman-Oppenheimer-Volkoff equations, written in 1939. The math existed, but solving the equations required data that researchers couldn't access. You can't safely extract a sample of a neutron star and examine it in a laboratory. Without physical evidence to test, physicists had to rely entirely on hypothetical models to guess how matter behaves when pushed to the absolute maximum pressure the universe allows. Because they could not touch the physical material, they had to reverse engineer the universe's limits using mathematical proxy data to finally complete the equations. To understand matter under such absurd pressure, researchers use a theoretical rulebook called the equation of state. This diagram illustrates two opposing versions of that rulebook that a team of Hungarian researchers recently deployed to test extreme matter. On one side, the SFHO model represents softer, highly compressible matter. On the other, the DD2 model envisions a tougher, highly rigid structural bond. Despite their differences, the researchers forced both models to obey one strict rule. Sound waves traveling inside the extreme matter cannot exceed the speed of light. Even in theoretical physics, imaginary models of superdense matter must still surrender to the absolute speed limits of the universe. To figure out which rulebook was correct, the scientists needed real-world space phenomena to stress test both the soft and rigid models. The first observational check came from the NICER telescope, mounted right here on the International Space Station. NICER maps the hotspots on rapidly spinning pulsars to precisely measure their dimensions. The second set of data came from deep space collision records. Massive Earth-based detectors, like the one housed in this concrete tunnel, captured the gravitational shock waves of two neutron stars slamming into each other, an event known as GW170817. Looking at this chart, you can see how the GW170817 collision data specifically allowed scientists to measure the physical squishiness, or structural deformability, of the extreme matter upon impact. When the team updated their calculations with both the telescope tracking dimensions and the collision data, both the soft and tough theoretical models crashed into the exact same mathematical wall, a maximum of 2.2 to 2.3 solar masses. By marrying distant telescope telemetry with the shock waves of colliding stars, they forced a definitive answer. Matter structurally fails at exactly 2.2 to 2.3 times the weight of our Sun. Based on this newly proven limit, the ultimate heaviest possible neutron star tops out at roughly 2.3 solar masses, compacted into a sphere just 12 kilometers across. This chart compares our limit against anomaly GW190814 at 2.59 solar masses. A neutron star this rigid violates limits proven by GW170817 collision data. Because GW190814 and anomalies like HESS J1731-347 break structural physics laws, they must be reclassified as black holes. The 80-year-old mystery is solved. We have successfully drawn the absolute boundary line between the hardest physical matter in the universe and the dark void that swallows it.